for the kind invitation. So this is my fifth talk, if I count the liquid crystal talk, and then in this school. So we're going to discuss structure, dynamics of biological liquid crystals. So I'm from the chemical engineering department. So the type of phases I'm going to be talking about today are rod-like nematic liquid crystals that display a nematic order. I put rod-like just because I want to kind of, at equilibrium, I want to describe uniaxial phases. And also cholesteric phases. Sometimes this nematic is called the N phase, and N star denotes cholesteric phase. So here we have orientational order fluid. It has no positional order, is an isotropic viscoelastic material characterized by an optic axis. So the simplest description of this system is the Q tensor quadrupolar order parameter that is composed of two parts. One is the scalar order parameter that changes with concentration for lyotropic and temperature for thermotropes. And this is a fast variable, a nanoscale variable. Here we have the optic axis, is the slow variable in the system. It usually describes topological defects, lives in the micron range. Many biological systems, which is the topic of this presentation, display the cholesteric phase. So here, in addition to this orientational order, we have a superposed periodicity. So on each plane we have an optic axis, and this optic axis changes slightly. We'll see some data. Typically for many systems there is a small molecular twist angle. So as you go in the direction of the helix axis, this optic axis rotates and defines a pitch. Here is denoted half pitch, the distance over which the director rotates by pi radians. So this system is periodic, is a layered system, is chiral because we have handedness, can be left-handed, right-handed. So, and the tensor order parameter that describes this system depends on space, on the z direction along the helix axis. And as we'll discuss in a minute, in the one difference, there are many differences, one difference between nematic and chiral nematics is the presence of biaxiality. So here, if my objects are rods, I have a uniaxial system, unless I put a field, electromagnetic field, or an interface or something. But here, at equilibrium without any external fields, we'll see that this system is biaxial, because the plane perpendicular to the helix axis, here denoted by L, is not isotropic. So I look at the plane perpendicular to the optic axis, and the system sees on the left molecules tilting up, and on the right molecules tilting down. So we have intrinsic biaxiality. So depends how excite or what I do to this material system, it can behave more like a nematic, or it can behave more like a smectic. Therefore, in this kind of systems, not only have disclination defects, but also dislocations as any other layered systems. Spectacular, I mean, at least for me, a spectacular manifestation of this layering is the so-called permeation flow, discovered by Johnson, Barat in the 60s, and explained by Helfrich. He was very prolific in explaining a lot of physics. So in this permeation flow, this is an example of capillary Poiseuille flow. P1 is the pressure at point 1, P2 is the pressure at point 2. So P1 is greater than P2. The helix axis is along the flow direction. And when you measure the viscosity, the low shear rate viscosity in the system, we have a value that is the apparent viscosity, is roughly 1,000,000 times bigger than a standard nematic viscosity. So this is so-called permeation flow. Of course, if you drive the system, this system is non-Newtonian, and at some point you can transform this helix into something else. So the viscosity will decay to the normal nematic values. But at low deformation rates, the viscosity is 1,000,000 times bigger, and therefore is a useful property for viscosity modification without adding any other components. And if gamma 1 is a typical rotational viscosity of a nematic, we have a geometric factor here, the radius of the pipe, divided by the pitch of this object, which is typically in the micron range. But if you have blue faces, that so-called double twisted faces, they can be sub-micron. So this number for a typical rheological device, whatever is 100 microns, 500 microns, and then you divide it by a number that, let's say, maybe 1 micron or 2 microns, you square that and you have a factor that is, 100,000 or 1,000,000. So very simple. And working out the physics of this effect is very interesting. As the material flow, this is steady state. So the only physics, the only dissipation of this is as you move, if you're a director and you move, so you're rotating, so that in this station you are vertical, and in this station you are horizontal. So we have steady state. So the only corrotational derivative that we have in the system is the velocity dotted with the gradient of the orientation. And in fact, sometime in the 90s, I forgot to put the reference here, and sometimes in the 90s I work out the structure. You can cast this problem, this permeation flow problem, as a Darcy law problem. So that's why you pick up this factor here. The velocity is a plug flow velocity. This velocity that results from this pressure drop can be expressed proportional to the pressure gradient, and this Darcy coefficient, if you will, is scales with the wave vector square.
Okay.
Yeah.
So in this case, you have a pressure gradient, P2
Yeah.
minus P1.
Yeah.
And
Yeah.
you're saying there's a plug flow which corresponds to this
Yeah.
rotation of the helix.
Yeah. There is some non-ideality.
I was going to ask about, so if we say it has non-slip boundary conditions, what actually happens?
Well, there can be other dissipation, kind of defect rearrangements.
So you get a thin layer where
You get a thin layer, yeah, the non-ideality, the boundary layer. Yeah.
Is it that the molecules jump from one layer to the other?
He said, okay, what's happening in terms of typical orientation at an interface? So they are adjusting. So this molecule, as it moves from here to here, this average ensemble of molecules is rotating. So if you sit here, the helix is always the same helix, is stationary. So the only thing that is happening is this so the key component in terms of dissipation or stress, viscous stress, is something called the corrotational derivative for vector type of model that looks like this. So the last term is the spin tensor, is the asymmetric part of the velocity gradient. And this is the convective part. And n, I will put n0. N0 is the director orientation that describes this helix. Because this is plug flow, this is 0. The symmetric part of the velocity gradient is also 0. Everything is 0. The only thing that dissipates, that contributes to this dissipation, is this term, v. So that's why at the end of the day you have an equation that tells you the velocity in the axial direction, the axis direction, is the pressure gradient with this. Q0 is the y vector of the helix.
Is it an activated process?
This is just
Well,
put a
I
pressure
mean that-
P1 and P2.
I mean that
The
viscosity-
rheologists, they put this in a little rheometer, and they turn on the angular velocity of the rheometer slowly, or in a capillary,
What
a
I mean,
pressure.
you would have
You mean if there is any,
viscosity would have Arrhenius dependence.
the viscosity of these experiments looks like this. This is an apparent viscosity. This is a flow curve as a function of Q.
No, I mean with
That's-
temperature. With temperature, is it would be Arrhenius dependence?
With temperature, I don't have the data in my head, how it works with the temperature effect, but we can discuss that later. They could be, I mean, many liquid crystals we know have, for example, yield stress, especially these cholesterics. They have a domain structure. So they have a yield stress, many of them, not all of them. But this is more or less the distinction. You never see this kind of viscosity values for a nematic, a chiral. So that was kind of an introduction. So the next point is liquid crystals in biology, nature. Why does nature uses liquid crystal? So this is a big discussion. Some people say, well, it's superfluous. Other people have said they are very important. I'm from the camp that if exist, it follows evolutionary path. There is a big role. So they are very important. So liquid crystals are structural, multifunctional materials. They self-organize. So we have silk examples of structural materials in nature. We have silk superfibers. So typically beta sheet. They are slightly different than the amyloids. So everybody is very concerned whether you want to have deposits sooner or later and develop kind of neurological disease. So this problem is somewhat related. The difference between beta sheets in silk is they align along the fiber direction, and the amyloids are transverse. So that's a key difference. But anyway, so this is one example, structural material. So we have multifunctionality. So examples are actuator sensor materials. So this is the outer hair cell of the inner ear. Long time ago, the explanation of these outer hair cells. The outer hair cells allow you to, here they don't send any electric signal to the brain, and they act as amplifiers. So the ear receives a sound wave. It creates ionic currents inside and outside the cell, which is consistent with the speed, the frequency of the sound. This fluctuating electric field then couples with the membrane. And this type of membranes are known as flexoelectric membranes. So you have flexoelectricity that tells you that the electric field couples with curvature. This is the difference. There is an intrinsic difference between flexoelectric and piezoelectric. Piezoelectric is where the electric field couples with the area, with the dilation. In this effect, the electric field couples with the curvature. So you can have, this is widely known, and the person that developed this field experimentally and theoretically is Petrov. Petrov has an excellent textbook on this subject. And so here, so now you have a fluctuating shape inside a viscous fluid. So the key point that we and many other people have worked this problem of this pump. So the sound wave creates an electric fluctuating field that couples with the membrane, and so you have oscillating membrane which is oscillating in a viscoelastic field. Viscoelastic. So what we found out is very interesting. So we have an enclosure. On one side we have one rheological fluid, on the other side we have a different rheological fluid. So we found out that to fine-tune a nice power spectrum that amplifies the incoming signal, you need a rheological contrast. So that was a key principle we found. So we also have beetle optics. Many people are studying the optics. We have cholesteric arrangement of the fibers, Bragg reflections, coloration, that's structural color production. So that's another area. So that shows multifunctionality. We have interesting problems of packing and ordering as in DNA solutions. Some people say, well, these are very short, 150 base pairs. Maybe, it doesn't describe actually biological situation. These are short helices. But anyway, this is very interesting examples. At low concentration, we have an isotropic state. At higher concentration, we go to a blue phase, which is a double helix in two orthogonal directions. At higher concentrations, we have a cholesteric phase, and at even higher concentration, we have an hexagonal phase. So at very high concentrations, the demand is to exclude the volume, and so this hexagonal phase does the job. And on this area here at low concentration, the demand is to satisfy chirality interactions. So this type of problems that you can see that the amount and type of orientational and positional order depends on concentration is one of the examples of this optimal packing. We have material manufacturing. Engineering, you think, is what's the best way to manufacture strong fibers with the least energetic expenditure. If you are a fiber like this, you have to take into account how much energy you need to produce your drag line silk, for example, to capture insects that might be around. So this shows a schematic of the duct of a spider silk. This part here, this is a gel type of system. Here we have stress-induced phase separation. Here you have a water layer phase. Upstream we have a liquid crystal. Maybe I don't have time to describe that today, but we have anisotropy in the system. And whenever you have anisotropy, and if you plot the viscosity as a function of concentration in the isotropic phase, you tend to have a divergence of viscosity. So you have high viscosity. As you increase the concentration, you go into an isotropic branch and you lower the viscosity. So the energetic demand of working at this low viscosity branch here is very favorable. So one of the key points is why nature uses liquid crystallinity. For example, this is a low viscosity process that produces a high performance fiber. We also have many types of directed self-assembly. A very interesting type of self-assembly, widely studied, is this chiral directed self-assembly, where you have a helix that grows from a substrate. And this type of picture is prevalent throughout nature. Is it's called biological plywoods, but the signature is when you take a cross-section of this helix, you end up with a texture that has these arc patterns. So arc patterns in many fibrous composites is the signature of cholesteric ordering. And Bulligand spent, according to him, like more than 20 years trying to figure out the connection between the cholesteric state and the arc patterns. It wasn't a 5-minute job. And he was very smart, Bulligand. So the classification of these systems in the literature are classified in terms of biological analogs. So these are solidified liquid crystallinity. And they are displayed by plant and insects, plant cell wall, connective tissue of mammals, exoskeleton of insects, bone, for example. The other big category is in vitro, so these are extracted, so these are biopolymer solutions that people do biomimetics or tissue engineering, for example, precursors. So here we have polypeptide cellulosics, viral suspensions in solvents, giving rise to pneumatic cholesteric phases. And we also have in vivo liquid crystals, so these are silk secretions, biological membranes, DNA in sperm. So there are many examples well cataloged in the literature. So we have a diverse range of geometric objects. Here we might have liquid crystallinity structure that forms from molecules to microfibrils to fibers to filaments. So you have a self-assembly process. But the common theme is that the effective or persistent length to effective diameter, these systems here, they are charged, they're semi-flexible. Taking into account non-idealities, we see that we have a large persistent or effective length to effective diameter that in most cases widely exceeds 10. So all these systems have been described by excluded volume driven transitions of Onsager type, plus the non-idealities of flexibility and charge I mentioned. So typically when you have a confined space and you increase your volume fraction by around 5 times effective diameter over length, you're going to have the transition. So some of the themes that I want to discuss here, but I'm sure I'm not going to reach, maybe I'm going to reach that point. But so the idea was to go back and talk about these 3 classes, say a couple of things about biological analogs. This is frozen in solid stuff. This is the precursors to tissue engineering, pick collagen, and say a couple of words about silk, but as I said, I won't have time. So the biological plywood, the key points I want to discuss is issues of chirality, the model that one can use, the Q-tensor model, and what is the physics embedded in this model when you add chirality, the types of kind of characteristic solutions to this chiral Landau-de Gennes type of model that describes observed phenomena in these frozen in liquid crystal polymers, and say a couple of words about this important topic of directed self-assembly and growth laws. So growth laws of how fast T to the 1, T to the 1/2, T to the 1/3, and what kind of defects people have cataloged, observed, and see if these defects people see in things in these biological plywoods are related to liquid crystals, synthetic liquid crystals defects. So the key idea here is, a lot of people, smart people before me for decades, work out very robust liquid crystal physics theories, and we want to see how much those theories can be leveraged to describe these biological fluids. And then I see point number 2. So, so biological plywood, so this is the so-called Bulligand texture, is cholesteric. So you have a system of self-assembly from molecules to microfibrils, fibrils, and fibers, and at the end you have this kind of chiral cholesteric structure formed by these macrofibers, if you will. And these form kind of protective layer in many systems. You have protective layer strength. One point with anisotropic, everybody loves carbon fibers, everybody loves Kevlar fibers. But the problem with anisotropy is you are limited to one direction. In nature, you have to, if you are a leaf, you have to deal with twisting and bending, for example. You have to support wind stresses, so forth and so on. So the solution, nature solution to this more generic type of stress field that a tissue has to support is this chiral structure. So here is moonbeam, celery petiole. So vegetarians, they eat a lot of liquid crystals every day. Root hair. So this is kind of crustaceans. Dermal scute of fish, bone, stiff walls of a pear, and in all these structures you can see the signature, which is the arc pattern. And these kind of length scales of these in this helix typically are in the micron range. Yes.
I'm trying to glue that arc with this little picture that you've got in yellow. The yellow picture is
Which yellow?
it says Bulligan structure.
Ah, the Bulligan.
That to
yeah.
me looks like this.
So the
Just
Bulligan,
the
so what happened is if you take a knife and you slice, if you are, let's say, an experimental biologist, right? You go with your sectioning instrument and you take a slice, right? And then you're not gonna cut this Bulligan structure right in the middle or right perpendicular to the axis.
But let me understand that structure.
Yeah.
To me, that structure looks like just a simple cholesteric helix.
Yeah.
Is that all it is?
No, yeah, there are a lot of variations. This is a cholesteric helix. I put it there because it kind of conveys the flavor of self-assembly. But if you want to see the whole manifestation in nature, there are perturbations to this. For example, this is a continuous angle. Many systems have discrete angles, even 90 degree. So you have kind of cubotic type of faces. So you have a fiber like this, a fiber like that, a fiber like that. Right? So this is a cholesteric arrangement of the fibers. Is that no?
What's a fiber and what's a molecule? Is the yellow thing a molecule?
No, that's a fiber.
That's an okay.
This
so it's like an
this
arrangement of a double
this is the
cylinder
pathway.
and something else.
This is the pathway. We started in the nanoscale. We are in the micron scale
Okay.
for this crab. You started here. This, for example, if it's this is chitin, but if this is collagen, this could be a triple helix. Right? The unit, the essential unit then undergoes self-assembly at several layers and cross-linking, covalent bonding. Yeah? No.
Okay.
So
I still don't understand, but I'll come talk to you later.
what, this process?
So the yellow fiber is made of molecules oriented parallel to the yellow fiber
Inside
inside it?
a fibril.
Yeah.
So it's like
Or
if
is
you
it
think
twisted
about,
inside?
so what you have here, the easiest way to think about is some kind of rope formation. There is some staggering,
Okay.
etc. But right, if you are a marine engineer, you have to design big, strong ropes
Mhm.
from strands. So that's a typical. You have small strands, thicker strands. And the interesting point is, in terms of chirality, is as you go from a primitive object, which, for example, is 3 molecules, so that's a coiled coil structure that assembles with another triple helix. That object is changing chirality from left-handed to right-handed. So each time you have this aggregation, you remain, the chirality remains but changes sign. That's a key concept here. The chirality doesn't wash out in this self-assembly. So a key concept here is that there is a molecular twist angle. So this is short fragment DNA. I know it's not the particular example I was describing before, but this highlights what happens when you try to pack chiral objects. So you're going to have a small molecular twist angle, an object twist angle. The angles, when you put them together, you minimize the energy, you're going to develop a twist angle. So for this short DNA, the twist angle changes with concentration. It's 0.5 degrees, so to speak. And this is an ongoing field. There is a lot of physics to describe this twist angle between objects. One of them is electrostatics. Here we have cylinders decorated with equal charge that describe a helical path on a cylinder. The pitch of the charge is H, and R is the diameter of this fiber, and L is the length of this object, and that's a predictive measure of this twist angle. This is a recent paper in Nature. Schaller and Bausch, maybe some of you know them, I don't know them, so there is an interesting Fusilli packing, okay? So these are observations in the supermarket. So in the center, this fusilli is pointing vertically at the edge of the package. It has a twist, so you have a twist angle. So this is another mechanism of packing, chiral packing, that gives you a twist angle, this geometric. And you can think on these supra objects, super fibers that pack and give chiral tissues. You might have these mechanisms at least. Now the other important object is, a point is that this is a frustrated mesophase. If you start with the origin is I, your destination is F, and if these objects that are packing, they pack with a small twist angle psi here, and if you follow the path BA, and here the path AB, and you compute what is the incongruency in the orientation, you find that you have an incongruency that is proportional to A cross B. And therefore, you will have to nucleate additional topological defects to pack this phase. So a way to resolve this kind of frustration, as explained by Oswald and Piransky, is to create this chiral mesophase. So small twist angle then gives rise to this cholesteric phase. The other point, as I mentioned, if you take the plane perpendicular to the optic axis n, you take a plane perpendicular, that plane is not isotropic. Therefore, in this phase plane that we introduced a few weeks ago, that describes all the possible ordering states S and P, the vertical is P, the horizontal is S. So all the possible states of this chiral nematic lives inside this triangle, and you can see that the plane perpendicular to n is not isotropic, so you have biaxiality. So the root that corresponds to a stable, homogeneous chiral nematic phase is going to live somewhere here and not on this line. This line was the P equal to 0 line. So I describe some more what happens. So to describe then chirality, to describe biaxiality, and also the topological defects that are observed, one can write down the Landau-de Gennes Q-tensor model with chirality. So we have an excluded volume term. We have a chiral term here, which is the curl of Q, plus a term that is proportional to Q. And here this describes splay, bend, and twist deformations. Now when you put into this expression here, you put this tensor, right? You end up with this kind of polynomial in S and P. This is the homogeneous part that describes excluded volume. U is a term that is called the nematic potential, which is proportional to the concentration of fibers divided by the critical concentration that describes the isotropic nematic transition. Is here I just wrote it in dimensionless form, but the key point I want to make here is that, so here we have the polynomial. Here you have S minus P squared that describes this chiral term. So if suppose I don't have any splay, bend, and twist in my system, and I said I want to minimize this free energy, here I end up, I go back to my triangle. Here I only consider one sector in this triangle, P and S. And there are two important lines here. This line, P is equal to 3S, we described before. This is the line where the topological defects live on this point. There is another important line, is this line P equal to S. So P equal to S is the chirality. This P equal to S red line minimizes the chirality. So I have a pitch here. If the pitch goes to 0, this term goes to infinity. So to minimize this term, P has to be equal to S. And if this line, is the chirality line, is the maximum biaxiality line that can exist in the system, maximum biaxiality. On the other hand, I have the excluded volume line that minimizes this term. So when P is equal to 0, as in a nematic, the pitch is infinity, so this term plays no role. So P is 0. So I'm minimizing the states, the nematic states lives on this line, P0. So here, all these curves denote what happens when I change P0 from infinity, so this is nematic, to 0, a fully biaxial line. So I move along these lines and I end up in this chirality line. And as I move, these different curves are curves corresponding to different nematic potential or more and more concentration. Okay, so this is the simplest effect of chirality to give you biaxiality. And the other important point is, some people say, well, who cares about chirality? I do my Onsager with electrostatics and flexibility, I'm okay. But the other point, you're missing the pitch, the effect of this pitch, P0. And if you take this simple free energy and said, okay, I'm going to forget about biaxiality for the moment, and right, and I still pick up here, I have a P0 from this part, and the key point then is the pitch delays ordering. So if you have shorter pitch, you need to put more and more fibers to create a nematic phase from an isotropic phase. So this kind of transition line, this is S as a function of nematic potential or concentration. So these vertical lines are going to be, if the pitch decreases, are going to be shifted from left to right. So, and many systems are, for example, we know blue phases have very small pitch. So as small pitch is also important. And with this term here, so now we have the entire free energy, the excluded volume. Yeah.
It goes directly from isotropic to chiral, or there's a little tiny window?
Yeah, there is window.
That's a little tiny window where
yeah.
P is equal to 0.
we have, in this formulation here, we simplify the formulation and said, we just want to look at S. We're going to, this graph is what is the effect of P0 on S. So the free energies are similar as the nematic. You have metastability of the isotropic phase, metastability of the nematic phase, but we have an effect of P0. So this is the value of the concentration of the transition. When P0 is infinity, you recover the 2.7 from Doi and Meyer-Sopi, etc. And when P0 is small, this concentration increases. Okay, so I'm not going to get far on this talk. So the key question then posed, in this part is, how does these bones and these tissues are formed, right? So what kind of the self-assembly of in the extracellular matrix, right? So that forms the connective tissue. So you can reason out, I have an Onsager phase ordering transition in the extracellular matrix. These are my fibers, my collagen, my cellulose, etc. So I have phase ordering in the extracellular matrix part. And I have chirality, so I expect to have a twisted plywood organization. Now, a key point is to have that uniform monodomain structure, you need definitive planar anchoring with a constraining layer. And without this constraining layer, you get these polydomain plywoods. And both are observed. So the key literature is by McGill, who wrote this textbook, Biology of Fibrous Composites. Sorry, I don't have the year here, is 93. Cambridge University Press. He devoted a lot of his time to study the connection between liquid crystals and these fibrous composites. So then we go back to computing the critical points of our free energy that has excluded volume, chirality, and Frank elasticity, and plot the critical points in our PS diagram. So we have a chiral root here. We have a chiral root there. We have a topological defect on this line P equal to 3s, and we have the isotropic phase. And we look at the connections between these three critical points. If there is no constraining layer, I have a connection between this chiral and defect structure, and you get polygonal textures through a mechanism of nucleation and growth. This is mantis egg case protein, is one example of polydomain plywood, right? And when we compute, this is one type of solution, so it's a nucleation and growth process. You can do, the topological defects, hepta, septa, type of grain boundaries, and etc. So it's all contained there. And the other solution is this connection, isotropic, cholesteric, and those are traveling fronts. So you put in your solution Z minus Vt, Q is equal to Z minus Vt. You plug it into your problem, and you get traveling front solutions of this type here. This is the kind of cholesteric phase. This is the isotropic phase. So you have a velocity that will depend, as I show you in a minute, on the pitch and other things. And at the end of the day, with this unidirectional motion that comes from strong anchoring, you end up with your plywood. So the 2 points is the directed chiral self-assembly. So if you do a little interfacial free energy, interfacial thermodynamics, so internal energy, entropy, adsorption, and your interfacial tension. You take the derivative of this object with respect to n, and then you transform your derivatives using Maxwell relations, and you find out that the preferred orientation, that is d gamma dn equal to 0, d gamma dn equal to 0, that's your preferred orientation, that's the orientation that minimizes the surface tension. So that gives you this expression that tells you that the preferred orientation in any system is a balance between energy, entropy, and absorption. And you can see here that the orientation at the surface can be manipulated with the chemical potential of a surfactant type, or wax type, or any other chemistry that insects and plants use. So, and also by temperature. So you can achieve changes in orientation and or determine strong planar orientation at a fixed angle using simple chemistry, which is accessible to the plant or the insect. The other point is the growth law. So here we have phase ordering. R is proportional to Vt to the first power. So V is a constant velocity, there is no mass transfer. Yeah, more complicated systems, they might couple, so might have order parameters, conserved, non-conserved. In this model, Q-tensor model, we have a non-conserved order parameter, so the velocity is a constant. You work out this expression of propagating front between cholesteric and nematic. The Landau-Degen equation gives you a constant velocity, which is a function of concentration, inversely proportional to the pitch. So the pitch resists the growth. And this intrinsic speed, if you will, is the characteristic internal length in the system, which is nanoscale, which is just the square root of Frank elasticity to CKT. And this is the rotational diffusivity for this rod. So as this front moves up, the rods have to realign. And that is described by a rotational diffusivity. And from polymer science, we know that the rotational diffusivity is very sensitive to molecular length, L to the 6. So it's not L to the cube. So L to the 6 is a high power. So you change this length, and you're going to have a strong impact on the speed. And so these are examples of slow growth phenomena in the periods of days for this mantis egg case protein. So the last point is there is always a big discussion in the literature. How do you know that this was that bones and all these structures, extracellular matrix, are formed by a liquid crystal self-assembly? So one point is look at all the topological defects and see if they correspond to the topological defects that one observes in liquid crystals. So this is a cholesteric structure that has self-assembled in the presence of these obstacles. This could be lumens or other channels inside plant cell walls, surrounding plant cell walls. So here we have mimic this kind of system with a colloidal liquid crystal type of problem. So we have a liquid crystal matrix, and we add the particles, and this result was obtained some years ago, corroborate experimental observations, that when you add particles, you have, for example, arrangements, they can be 4 or 5. The kind of texture particle rule is that the charge is, for this tangential case, is the number of particles minus 2 over 2. So when you have 4 particles, you're going to have a -1 defect, and when you have 5 particles, -3.5. So this defect charge rule, we call it the Zimmer rule, because Zimmer did all his work when he was a PhD student in UC San Diego, and did painstaking work with carbonaceous type of mesophases. So he did all these experiments in the 70s. But the other interesting point that he observed too is the type of core. The core it has an even-odd effect. odd number of particles give you singular core defects. So this defect here is a singular, and even type of particles, they give you the escape. There is no singularity. The rods or the disks escape into the third dimension. So here we have 4 particles. We would expect then a -1 defect and an escape core. So this is what we predict is so-called cholesteric lambda line defect. All right, so we did other things, but I think that's what I want to say. Now, for cholesteric collagen solutions, there are a lot of interesting issues, and there is more data. So these are in vitro type of liquid crystals. So the key point is maybe this helps a little bit. This kind of triple helix and protofilament and monofibril, fibril, so it's kind of hierarchical structure. But then this collagen fiber orders in a cholesteric symmetry, the fiber. But what is interesting is I have to give credit to this paper, Gobo, Langmuir, 2007. So this is French group, Giraud, Gilles. So they did a very extensive, they've been working on this for decades now. So in this paper, there is a very interesting kind of summary of thermodynamics, defects, and rheology. So all together. So I found that this complete description was very useful and challenging. So what they did is then they work with rat tendon extraction. So somehow they extract the triple helix, they use acidic solutions, right? And that solution is what you see here, is a cholesteric liquid crystal of the triple helix, right? So it's a polymer solution, if you will, right? So they did this rheology and film processing because the end goal is trying to mimic these structures for tissue engineering. Prime examples are artificial cornea, for example, or artificial muscle. So if you come up with ideas of artificial cornea using the same type of material architecture that already exists. So that's kind of the strong interest. So this is the phase diagram. So these are acid solutions of these triple helix collagens as a function of collagen concentration in milligrams per milliliter. So the key point is there is a transition line here. To the right of this transition line, I have a cholesteric phase. To the left, I have an isotropic phase. The numbers typically are 50 to 80 or 90 as we have a transition from isotropic to cholesteric. Not determined experimentally, there is a band where you have biphasic equilibrium. So here you have biphasic equilibrium, and inside the biphasic equilibrium, like in other liquid crystal systems, you tend to have tactoids. So that I put the tactoid there to show the fact that in this chimney, if you will, like this kind of chimney structure, that's where you have tactoids. They are stable, they're not going anywhere, they're micron size, they're stable. They are anisotropic, they have orientation. Depending how you prepare the system, you can have positive tactoids or negative tactoids, depending on whether you come from isotropic or nematic phase. And we have a nice fingerprint type of cholesteric texture with distinctive topological defects. So this line, kind of a vertical approximation of this line, can be captured with modifications of Onsager theory that introduce charge effects and flexibility to the critical Onsager concentration. And so again, this Onsager transition is driven by minimization of excluded volume. Here the excluded volume is L squared over D, L is much greater than D. Here is LD square. So you decrease the excluded volume and you enter into an ordered phase. Matching these theories with their modification to the phase diagram, you end up with a persistent length 50 to 150, effective diameter 4 to around 4. So the key point of this exercise here is that L over D is very large, around 15. So that number is very important, L over D, for the rheology and other things. Other effects that have to be taken into account is solvent rod interactions. So these kind of phase diagrams that can be constructed by modifications of Meyer-Sopi type of models. Kate did some work some years ago with Matsuyama and for this kind of phase diagram, and we have explored this type of chimney formation. So as you increase molecular weight, some interaction parameter, this chimney is attached to the zero axis, to the y-axis. And the key point is trying to understand, how you disentangle this little chimney that is attached here and make it vertical, which is more in agreement with, at least with many liquid crystal polymers. So the other point is, okay, so this is the texture, you have some topological defects. Does it follow topological defect physics of synthetic liquid crystals? So here are some of the disclination and dislocations observed, typically are described in terms of lambda lines, which are, the core of these lines are non-singular, so they are energetically less costly than these tau lines that are singular. So for DNA, this has been extensively studied and cataloged, and the relative abundance of lambda lines versus tau lines has been established. And because we also have layering, we have dislocations in this system. So the relative easy of nucleating defects is given by this penetration length, which is the square root of the bending modulus to the bulk modulus, and this penetration length is related to the amount of strain you need to bend a layer, and these numbers are less than the pitch of the system. And the key point here is that this penetration length decreases the density, the facility to nucleate, and disclination, dislocations increased. And if we look now at the data of Giraud-Gilles for collagen triple helix, there are some key signatures, like this cone here is illustrated in this diagram here, and this is lambda 1/2. This is older literature, they call it lambda plus, but it's a lambda plus 1/2 disclination right there. So these triple helices behave as one would expect. The other point, my time is running out, right?
Yeah.
Okay.
Make the rest optional.
So the whole point is, what's the rheology? So the key point now is this, when you do capillary suction, yesterday we were hearing capillary suction, when you do capillary suction with a cholesteric phase, you generate capillary flow, so this is driven by this impregnation factor, and with this kind of capillary flow you can generate sufficient shear rates and to destroy the helix. So here you have helix unwinding, you unwind the helix, and this is an interesting problem, mathematical problem. I tried my best in the 90s, and we found it very simple, the simplest case. We put the helix along the perpendicular to the page and produce a shear flow perpendicular to the helix, and the most basic free helix response is to have pitch expansion superposed to rotations. So you have like traveling wave modes, and so this thing is rotating and is expanding. And so you have this process of expansion gives you a divergence of the pitch at a critical shear rate, which scales with the orientational diffusivity. So you have a lot of shear rate in the system to melt the helix and turn it into a nematic. So now you have a nematic and you do nematodynamics, right? And so the key point, you do nematodynamics like we do, flow-induced orientation, right? You introduce a flow and you create a flow-induced orientation. So this is a useful approach in the isotropic phase. So introducing flow-induced orientation in the isotropic phase give you a so-called paranematic phase. That was the first experiment. And the second experiment is, again, do cone and plate rheology, but in the nematic phase. So the key point is this. We talked about L over D. So, sorry, I just want to say something here. The simplest nematodynamic problem, flow problem with nematics has 4 parameters. One is the concentration, the other one is the ratio of time scales, and the other is the ratio of length scales square. And the 4th parameter is so-called shape parameter, beta, which controls the coupling between flow velocity and Q tensor velocity. This beta is positive for rods, negative for disks, forms part of the critical tumbling parameter, lambda. So the tumbling parameter is proportional to the shape parameter, and then you have an ordering function in terms of scalar order parameters. But the key point is, how do you measure this beta parameter? Some people say, I don't care, beta parameter is L over D minus 1 divided by L over D plus 1. So that doesn't describe reality, there is more complication. So you're better off to investigate the value of this beta. The key point is that for system lyotropic rigid rods like Kevlar, polybenzyl glutamate, these large L over D values give you a tumbling parameter less than 1, and the system tumbles in shear. And for things that are more floppy, like copolyesters, etc., these L over Ds are lower, much lower than 80 or 16. So these are semi-rigid polymers. This tumbling parameter many times is greater than 1, so they flow align in shear. So the key point is, if collagen triple helix from thermodynamics, we say that this L over D is 14 or is much greater than 10, it belongs to this class of polymers and should behave like a Kevlar polymer. It should tumble in shear. So that's what is observed in the isotropic phase, the rheology. In the isotropic phase, we do paranematic phase by shearing the system in the isotropic phase. And these are Sachs experiments, no flow, you have isotropy, flow, you have anisotropy, this is the scatter intensity, and out of this you plug into this formula and you get the scalar order parameter that goes from 0 as a function of shear rate and goes all the way up and eventually saturates around 600 reciprocal seconds. The value of the scalar order parameter is around 0.4. So this is a paranematic phase, shearing the root in the isotropic phase. So we do our simulations, and this is the experiment, this is the theory, and we compute the Q tensor parameter. So we have a scalar order parameter curve that increases with increasing shear rate, just like in the experiment, and we have an orientation vector that decreases from 45 towards low values towards 0. So this ellipsoid isotropic ball tilts and deforms towards the flow direction, showing that the shear rate affects the two things, the scalar order parameter and the direct orientation simultaneously. From this curve, matching two experiments, as indicated here, matching to these experiments, and using our theory, now we have a tumbling parameter as a function of concentration, and find that we start here, the root is here, therefore the reactive parameter is greater than 1, and these things don't tumble in shear, they flow aligned. Okay, now we are stuck. We bet that this is our tumbling function. We already did this in the isotropic phase. We put the money on the horse, so to speak, right? So this is the tumbling function, and now I'm going to take the system right here in the cholesteric root and shear it and see what happened, right? So this is a long story, but this is the ratio of length scales as a function of shear rate. And so this kind of summarizes what happens if you have a tumbling kind of system. Perhaps you've seen in the literature, a lot of people got very famous with these kind of transitions from tumbling to oscillations to flow alignment. But so this plot of length scales ratio to shear rate is divided into 3 parts. Very low shear rate part, you have pattern formation. Then you have a parabola here, you have out of plane modes, and then you have outside this parabola a high shear rate, you have back to in-plane modes with all kind of bifurcation cascades that were discussed in this meeting and previous meeting, I think in the liquid crystal meeting. The key point, you have pattern formation here, band formation. So now we have collagen should predict band formation. So this is what is observed. The collagen, the sheared collagen solution at low shear rates in a gap in shear cells in the micron range give you nice pattern formation bands, as you expect, perpendicular to the flow direction of a characteristic length scale, which scales with the gap thickness. And this we done the whole pneumatodynamics and solve for the Maxwell equations and compute the optical response and fit very nicely the optical response with the optical bands. These bands are observed between cross polars. So you see these bands perpendicular to the flow direction. So in this case, this was the same tumbling function we had before as a function of concentration. We started a high concentration, this part of the phase diagram. We shear, we should tumble. But because the shear rate is low enough, we have 3-dimensional organization. It's a long story. I don't have time to explain, but it's a suspension of defects that gives rise to very well-ordered patterns that describe the bands. So I think with this is so where we going from here? I think I just maybe wrap it up. I think it's more outlook. I think there is a lot of things for younger people. Well, I'm not retiring tomorrow, but there is a lot of problems here. So liquid crystal science and biology, morphogenesis, is always going to be around. These problems of functionality, like hearing, for example, where you have new mechanotransduction. We have a lot of packing problems, self-assembly problems in biology that haven't been explored completely. You have flexibility, you have charge. So very rich area. You have this biomimetics field, so if you want to produce structural materials like strong fibers, we can look at silk spinning, for example. This is energy harvesting, for example. We have used this concept of flexoelectricity membranes to harvest mechanical energy. So the ear, like the inner hair cells, use mechanical energy to create a voltage. So this voltage then can be used as an energy harvester. So a lot of people are looking at energy harvesting systems. So here is harvesting using flexoelectricity. And this area, hybrid liquid crystal materials, for people interested in medical applications, liquid crystal sensors, liquid crystal in medicine, is full of new problems open to mathematicians and physicists. Thank you. I'm just 10 minutes late.
Some brief questions. We postpone questions to the coffee.
Coffee or beer?
Yeah, or later to the meeting. So we
Yeah.
started 6:30.
6:30, right?
Yeah,
Okay.
in the lobby, essentially. But I mean, I sent the link with a plan where we should be around 7:30.